Hello, welcome to Deterministic Optimization. I'm Shabir Ahmed. I'm one of the co-instructors of this class. So today we're going to review some properties about sets. Let's get started. So our learning objectives are to recognize the kind of sets that arise in optimization problems and then recall some properties of sets. Let's get started. So remember that we've talked about that the generic optimization problem involves optimizing we talked about minimizing some objective function of variables x, which is the vector of decision variables, where the values of the decision variables are constrained to lie in some set, capital X, right? So that's what this symbol means, that the vector x that I'm seeking, whose values we are seeking, is an element of this constrained set or feasible set, okay? So here, again, just to remind you, here x is the decision vector whose values are constrained to be in the set capital X. Typically, this capital X set is going to be defined by domain restrictions on the variables, right? So such as this. So X is an n-dimensional vector. That's, you can think of it as a domain restriction. And a relationship between the variables specified by inequalities or equalities, right? So we would have something like this, right? So we'll have a function gi whose value gi of x should be less than or equals to bi. So I'm only interested in those values of the vector x for which the function value is less than or equal to bi. There could be equality constraints and so on. And there would be kind of more than one of those kind of constraints, maybe m here as noted. So here x is the set of solutions to the specified inequalities. Okay. So let's look at an example. So here we have a very simple two-dimensional optimization problem. We are trying to minimize x plus y square. So our decision vector is this two-dimensional object xy. And we have two constraints, x plus y greater than or equals to 2, and x squared plus 2y squared is less than or equals to 8. So it's two-dimensional, so we can actually draw out the constraints, right? So here, let's draw the first constraint. X plus y is greater than or equals to 2. That's the line which says that x plus y is equals to 2. And my solutions are the ones for which x plus y is greater than or equals to 2, which is kind of this part, right? This is, here are all the values for which x plus y is greater than or equals to 2. The second constraint says that x squared plus 2y squared is less than or equals to 8. So here, this ellipse is the equation for x squared plus 2y squared is equals to 8. And now I'm interested in values for which it is less than or equals to 8. And then this is this set of solutions, right? So everything that's on this side for which the coordinates x and y are satisfy this inequality. And since we have to satisfy both of those things, both of those constraints, our set of feasible solutions is the intersections of these two regions, which is this part here, right? That's the intersection of those two constraints. That is the set of solutions that we are interested in. So we'd like to optimize this objective function over this set of solutions, okay? So now let's add a domain restriction on my variables, right? So now we're going to say that we are only interested in vectors whose coordinates are integers. Remember that this is the set of integers, right? So we are only interested in, we have exactly the same constraints as before. Now we just added a domain restriction that the coordinates must be integer numbers. So if you look at the set of solutions which we had before, and we look at them and we look at all the integers that are contained in the set and which are denoted by these little circles here, right? Those points. Those 4 points are the only integers in this set of solutions. So there are only 4 solutions to this optimization problem, right? So this, and that. 4 feasible solutions. Among these solutions, you can plug in check the objective function value and find out which the minimum is. Okay? So this gives you an idea of what the sets that arise in an optimization problem looks like. So let's go on and define some concept about sets. So a set is going to be called closed if it includes its boundary points. So this is kind of an informal definition. We don't know what it means to be a boundary point, but here's a formal mathematical definition. A set X is closed if for any convergent sequence in X, if I take a sequence of points in X which converges to something, its limit point also belongs to X. In other words, mathematically, if I have a sequence which is entirely contained in X and it converges to something x0, this sequence, then this limit point also belongs to X. Then it would be a closed set. So if this test fails, then it would be not a closed set. So here's an example of a set that is not closed, right? This is a set of points for which x squared plus y squared is strictly less than 1, right? So for example, if I take a sequence of points here, which is converging to this point over here, right? So that's the limit point. So the entire sequence is contained in my set, but the limit point, which is on the boundary, because I do not have the equality, it is not contained in the set, right? So this fails the sequence test that I just talked about. So some examples. So the set, let's say the entire plane R square is closed. Okay, so of course, the entire plane does not have any boundary points. It's not a bounded set. So if I take any sequence of points and which is convergent, then its limit point must be included in there. So that's why it is closed. Here is a set which is just on the real line, which is kind of an open, an interval that is open on one side, so an interval that looks like that, right? The set of these points. This is not closed, again, because if I take a sequence of points, so let's actually write down the sequence of points. So let's take this sequence, 1 over I, right? So this is my sequence of points. So I know that the limit of xi is equals to 0, right? However, 0 is not, so every x such as this xi is going to be in this set, right? However, 0 is not contained in this set. So I've just constructed a sequence of points which has a limit, but that limit point is not in the set. An important fact, intersection, at least finite intersection of closed sets is closed. Okay. Typically, remember that we are going to encounter sets in optimization problems. And if your optimization problems have inequalities, and none of these inequalities are strict inequalities, so we are always going to have less than or equal to as opposed to strict, then this set is typically closed. Right? So this is a kind of an informal check whether the set involved in your optimization problem is closed or not. Let's talk about a bounded set. Right? So a set is bounded if it can be enclosed in a large enough hypersphere or a box. So in other words, what does that mean? That a set is bounded if there exists a large enough number, non-negative number m, such that every element of that set has magnitude less than m. So m is fixed from before, and every element in X has magnitude at most of size m, right? So here is a set, and you can see that if I look at all the elements in the set and I can measure its magnitude, I can enclose it in a large enough ball, right? So the magnitude of any vector in X cannot exceed this the radius of this, assuming this is the coordinate, the radius of this ball. Okay, so that's called this is how these two definitions are related to each other. Okay, a set is going to be that is both bounded and closed is called a compact set. Okay, let's go through some examples. So in the first example, we are talking about the plane, the two-dimensional plane. Such a set is closed, obviously, because if you take any sequence of points that converges to a limit point in the plane, that limit point must be in the plane. But such a set is not bounded because the plane, you cannot enclose the entire plane in a large enough hypersphere or a box. Let's look at the second example. We've just seen this before. This is the set of points, again in two dimension, which are inside a circle of radius 1, except that the circumference or the boundary of the circle is not included. Such a set is obviously bounded because any vector from this set has magnitude at most 1, but it is not closed because the boundary points are not included. Here's another set which looks like, so this is again in two dimension. We have the line x plus y equals to 1. We are interested in the set of solutions for which x plus y is greater than or equals to 1. That's the shaded area. This set is obviously is closed. Again, it involves only a greater than or equal to constraint, but it is not bounded. A fourth example. So here now we have the set of points in a circle of radius 1. Including the boundary points. So clear that set is obviously going to be closed, and it is bounded, right? Because the magnitude of the vectors in this set is at most 1. So this set is now is called a compact set. Remember just the definition that a set is compact if it is both closed and bounded. Okay, so let's summarize. So we talked about sets because the decision variables of an optimization problem are constrained to be in a set, and it's important to understand some properties of these sets. So the sets that show up in an optimization problem are defined by domain restrictions and inequalities or equalities that relate the variables together. So please remember the definitions of closed, bounded, and compact sets as they will show up in the next lectures. See you next time.